You guys have had chemistry in high school, but you may not have covered this, okay? And or you may have covered it and it wasn't to the depth that really you understood it. So I'm just putting that up front there, okay? So Unit 3, we're going to be talking about energy and the transfer of energy. We're going to be doing some labs where, of course, you can't see energy, of course, but we can use thermometers to see the energy being transferred, thermal energy being transferred, so it's kind of fun. And it's a basic part of understanding physical science. So this particular topic, sometimes you'll see it in physics, sometimes you'll see it in chemistry. So there definitely should be an overlap. So thermodynamics, the word dynamic means moving. So thermo means energy. So thermodynamics is looking at the movement of energy, specifically thermal energy. And again, we don't really see it, but we can use a thermometer to kind of see where it's gone. Okay. What is energy? Energy is the ability to do work and or transfer heat. So we can kind of break energy out into different types of energy, forms of energy. We can also kind of take energy and say energy is either potential energy in which it's stored, or kinetic energy in which the energy is actually being spent. Kinetic energy often associated with motion, kinetic energy. Okay, so we have potential, stored energy, kinetic energy, energy associated with motion. So here we have a waterfall. In a minute, the next slide I think is going to actually show you where we can use moving water like this to ultimately create electricity. So the way this is showing you potential energy and kinetic energy. So up here, I'll put PE for potential energy, okay? So as that water gets ready to go over, with regard to how fast it's moving, actually it's moving the slowest up here. And due to the gravitational attraction between the water and the earth, as it free falls, it goes faster and faster and faster. So actually then, down here, it has the most kinetic energy, most KE. And up here, it has the most PE, potential energy. So one of the things I think we've talked about here is the conservation of matter. You know, when we balance equations, we're counting on the fact that no atoms are created and destroyed during a chemical reaction. We also have an important thing going on in our universe, conservation of energy. So in this case, we are actually converting potential energy into kinetic energy as we do this. So here's the picture of the power plant. So up here we have the water. I don't know if you can see the water here. Here we have the dam, and within the workings here would be converting potential energy into kinetic energy, specifically, as the caption says, to that kinetic energy is moving a turbine, which that turbine then can create electricity. So energy is the ability to do work and or transfer thermal energy. So we've been talking in here about English. Is that too bright, Madison? Okay. It's a little bright. We've been talking in here about English units and metric units. And as it turns out, the calorie, like you kind of link it to the calorie you read on the back of our candy bars, okay? But the calorie is an English unit, and a joule is a metric unit. And what I think works out well is I'm going to put a little picture here, and we're going to be talking more about the transfer of thermal energy. This is going to be a block of material. Specifically, this is going to be water. Specifically, it's going to be 1 gram of water. So by definition, this is kind of fun. This is something that any little experiment somebody can do on their own. If you want to know how much energy a calorie is, you take 1 gram of water, and its initial temperature, I'm just going to put T sub I for initial temperature, is going to be 14.5 degrees Celsius. And its final temperature, T sub F, is going to be 15.5 degrees Celsius. Of course, the change in temperature is 1 degree Celsius.
And then here's the zapping part. Zzz, this is my zapping energy. So this is energy in, and that's equal to 1 calorie. 1, and I'm going to put a lowercase CAL, the abbreviation for a normal thermodynamic calorie is lowercase. Well, that's kind of fun. Notice it says at one time, that was the definition of a calorie. Now a calorie is linked to a joule. What does it mean when we say there's an exact relation? In a minute, you're going to see I have a little table of different energy units. And it says 1 calorie is exactly equal to 4.184 joules. What does that mean? There's no uncertainty, exactly. That's a big, hairy deal. The abbreviation for joules is going to be J. So now back to the candy bar, your Snickers candy bar. They also say calories, but they're going to be in uppercase CAL. And the way this works is our candy bar calorie is a dietary calorie, and it's equal to 1,000 thermodynamic calories. Okay. So again, uppercase CAL for the candy bar calories, lowercase CAL for the ones that we're going to be dealing with. What do you think? I don't think it says on the slide, but is there an exact relationship between 1,000? So 1 big calorie, I'll put it here. 1 candy bar calorie or dietary calorie is equal to 1,000 calories. Is that an exact relationship? Yeah, I don't think it says it up here, but it is. Totally. All right. Well, a joule, and it's weird to see that like in lowercase Joule. Actually, to abbreviate it, it's a capital J. And I can draw a picture for this too. If you want to know what a joule is, then all you got to do is take a 2 kilogram mass. So here's my box again. In this case, it's not 1 gram of water. In this case, this is a 2 kilogram object. And I'm going to move it this way. And V, its velocity, is going to be 1 meter per second. 1 meter per second. Now, associated with motion, that must be kinetic energy, not potential energy. So that's kinetic energy. One of the ways we can narrow down into how much kinetic energy that object has, and it's coming up on the next slide, so maybe you guys have known this, but KE is equal to 1/2 mv squared. So all we're going to do is like plug and chug. That's a physics equation. We're going to chug the 2 kilograms in for the m, and for the v, we're going to square that term, and it's going to be 1 meters per second. Of course, the 1/2 kind of takes care of the 2 kilograms, makes it 1. 1 squared is 1, so you actually have a value of 1. So specifically then, the kinetic energy associated with that moving 2 kilogram object is 1 kilogram meter squared per second squared. That's what you get when you plug those values in. And that's equal to 1 joule, capital J. Joule is the basic unit in the International System of Measurements of energy. Yeah, and the joule is an uppercase J. So, because remember, with all of these abbreviations, they are case sensitive. So kinetic energy is 1/2 mv squared. So in that little example, I plugged 2 kilograms in for the m, and for the v, I plugged in 1 meter per second. Oops, second. All right. That was kind of an aside a little bit, although I do think when I showed you the definition of 1 calorie, and thermodynamic calories, 4.184 joules, you're going to want to memorize that. And also, I like the zapping. I like the 1 gram of water, zapping it with 4.184 joules or 1 calorie, and raising it 1 degree Celsius. When we get going in these sort of problems, you're going to kind of want to picture that sort of thing. All right, so things you need to memorize. Memorize. I'll put a little arrow here. 1 calorie, by definition, is 4.184 joules. And then we have this sort of thing going on with regard to the big C means thermodynamic. Sorry, big C, this is a dietary. And this is thermodynamic. I always like to think, so if it's candy bars, like, oh, one of those jumbo ones can be like 1,000 calories. So, but that's thermodynamic. Oh, sorry, that's dietary. So, oh my gosh. So if it's 1,000 calories, big C, then it must be, that's not good. Like 1,000,000 calories, thermodynamic calories. Oh dear. Love those candy bars. Okay. So we're going to revisit this idea that all matter has motion, okay? And honestly, if this is a thermometer and I stick it into water, okay, that thermometer is measuring the motion, okay, of the water. So that's the motion spoke of here. So thermal energy is not the same thing as temperature. So this is my thermometer, okay? This does not measure thermal energy. This measures the temperature of those particles. And I don't know if we'll get to it Wednesday or it might be Friday. No, we don't have class on Friday. But in order to know how much thermal energy an object has, not only do we need to know its temperature, but we need to know how much matter we have. And then we also need to know a characteristic of that chunk of matter that we're measuring the temperature of, called its specific heat. Okay? So 3 things in order to say how much thermal energy an object has. So thermal energy and temperature are not the same thing. Thermal energy is the kinetic energy. And we measure it using a thermometer, but we only measure the temperature, not the overall thermal energy. So when we talk about the amount of thermal energy anything has, a chair, a desk, a cup of hot water, okay, think of basically the thermal energy is a function and is indicated by the motion of those particles. And of course we can gauge the motion of particles by a thermometer, but not the overall thermal energy it has. So this is a video that we watched before. I tried these at my office and they worked fine. Hot and blue is for cold. How else can we tell these red ones are hot? If you're colorblind, well, that can't tell. By the figure, indicated by the figure.
Vibrations.
Yeah, the vibrations. And it's kind of trying to show you more vibrations with kind of the more little ringlets. Isn't that cute? Clever. Okay, so here we've had these hot, fast-moving particles and these cold, slow-moving particles. So the study of thermodynamics is the study of how thermal energy is exchanged between 2 objects. Okay? So basically we're going to take those 2, they're isolated, and we're going to open a gate between the 2. Okay, and as we open a gate between the 2, this actually is one of the basic laws of thermodynamics. And this to me makes sense. We have hot over here, we have slow over here. Okay, we open the gate. Doesn't it make sense that, and they're fluid, it's either a liquid or a gas. They aren't solids, they're fluids. So they're actually going to exchange positions, kind of flow into each other. But these guys are going to get, okay, and they're going to smack into these guys and they're going to make them go faster. Now, in doing that, in that collision, these guys are going to slow down, and these guys are going to speed up. So you kind of have that mixing going on, right? And you've seen this before, like if you were to do this little experiment at home, it will reach one common temperature, won't it? Isn't that kind of fun? We're going to call that a type of equilibrium. It's kind of just that. Everybody's all kind of got the same. These guys slow down and cool down. These guys sped up and warmed up. So what I just described is the direction of heat flow, heat transfer. Heat's going to be transferred from the hot to the cold. Kind of makes sense because they got all the kinetic energy going on. I know it sounds opposite, like we're going up on some colder days. When you open up the door, you're like, oh, dude, all that cold air comes rushing in. Well, it is, but actually it's because a vacuum has been created by the warm air rushing out. So it's not that the cold air is being more aggressive because the warm air is rushing out and creating that gravity. So anyway, that's how that works. So I kind of tried to explain this, that this is my thermometer. I know it's not a thermometer, but we're pretending like it is. That this thermometer will tell me a temperature.
And by golly, it is an indication of how fast how much kinetic energy that matter has that it's interacting with. But that's not the whole story with regard to how much thermal energy that object has that thermometer is measuring. It's one piece of actually three, to be specific. So temperature and thermal energy are not the same thing. Thermal energy and heat content are the same. Okay, so heat and thermal energy, yes. Temperature and thermal energy, heat, no. So clear back in Unit 1, we talked about different properties, chemical properties, physical properties. We talked about intensive properties, independent of amount, and extensive properties that do depend upon amount. And as it turns out, temperature, what your thermometer is reading, is independent, so it's intensive. Okay. Case in point, if I got a cup of boiling water, or if I have a big pot of boiling water, okay, of course it's going to boil at 212 Fahrenheit, 100 Celsius. That's it. But which one has more thermal energy, my cup or my pot? My pot. And why is that? Because it's amount. There's more. Exactly. There's amount. So temperature is intensive, but heat or thermal energy is extensive. So temperature, you need temperature, and I told you three quantities. What else did I say? You need to know temperature, you need to know amount, and you need to know something, what we call as specific gravity, specific heat, or heat capacity of the matter. Spontaneously, we kind of talked about this before. Thermal energy is always going to go from your hot to your cold. It makes sense. This little video has a little bit of sound to it. I'll tell you what I'm telling you. From left to right, we kind of see what's going on. Here they're separated. Here you let them into contact. They're showing you, according to the law of thermodynamics, thermal energy is going to be transferred from the hot to the cooler. And then given time, if you these must be what, purple? So red, blue, and they kind of, the red slow down to purple, the blue speed up to purple. Thermal equilibrium. So one last thing we need to talk about are temperature scales. Honestly, in your labs in here, we're going to stick with metric. So that means Fahrenheit's out. But I'll tell you, usually if you're wanting to know what the temperature is like outside, you're going to go Fahrenheit, which is in English. We're going to go metric, which is Celsius. But I'm going to also introduce you to a second metric, which is from Celsius, we can go actually Kelvin. I'm going to talk about those three temperature scales. So Fahrenheit, we're going to kind of compare the main temperatures at which water transitions under 1 atmosphere pressure anyway. Water will boil at 212 Fahrenheit and water will freeze at 32 degrees Fahrenheit. That's assuming it's pure water. Actually, we get into that in Gen Chem 2. This whole idea of why do we put ice on the roads to get the water to melt. So the Celsius temperature scale, like I said, is metric. Fahrenheit is English. So on the metric temperature scale, Celsius temperature scale, we kind of have some nice, neat numbers with regard to the transition temperatures of water. Water will boil at 100 degrees Celsius and water will freeze at 0 degrees Celsius. So right away, you kind of have two temperatures that go together. So the 212 Fahrenheit goes with the 100 Celsius, the 32 Fahrenheit goes with the 0 degrees Celsius. So here's the two temperatures scales I've been talking about. Notice, and this actually, I play a game, I have an app called, I haven't done it recently, but it's called Quiz Up, I think Quiz Up. And they have different categories, and one is chemistry, and this is like one of the questions that comes out when you play against people across the world. Quiz Up. But anyway, on these two scales, check this out, -40, the answer is -40. What temperature on the Celsius and Fahrenheit is at the same number? -40. Isn't that cool? I guess so. So another temperature scale we need to talk about is the Kelvin temperature scale.
Now the Celsius and the Kelvin are directly related. They are both, I'll put M here for metric. I'll put metric. They are both metric. And they are offset by 100 units. So in chemistry, I said in chemistry, we're really gonna be dealing with Celsius. I need to change that up, especially when we start dealing with gases. The temperature scale we're gonna do is the other metric. We have to actually, not Celsius, but we need to talk about the Kelvin temperature scale to work problems. So I want to kind of pick these apart, kind of talking about scales. But before I do that, here's another comparison. So we have the 3 temperature scales here. We have the Fahrenheit, the Celsius, and the Kelvin. And I told you the Celsius and the Kelvin are offset by 100. So down here, when you're looking at 30 degrees Celsius, that's 303, which is 100. Actually, it's 273. Let me go back. Oh, I suppose. The units are the same. They're offset actually. I'll write it here, offset direct by 273.15 units. So they're just saying that 100 units here is equal to 100 units here. I was like, that doesn't make sense. Okay. One of the things, I'll go clear down here to cold temperatures. I would call negative 321 Fahrenheit pretty darn cold. Its corresponding Celsius temperature is negative 196. Its corresponding Kelvin temperature is 77 Kelvin. In terms of like outer space, how cold is it? If you get out to Pluto, the dwarf planet Pluto, you're looking at, it has different ranges depending upon what side of Pluto you're talking about, but somewhere between like 11 and 5 Kelvin. That's how cold it is out there. And you probably know, if you remember from the Kelvin scale, once you get to 0 Kelvin, the thing there is that all molecular motion stops. And then you've kind of come to a quandary. Well, if all matter has motion, and the motion of all matter has stopped, does it really matter if it doesn't have motion? You know? The point there is actually we have, in the lab, cooled things down to approaching 0 Kelvin, but not reached 0 Kelvin. Makes you want to do it, doesn't it? A few years ago, they came out with a report that actually 0 Kelvin had been attained. And if you look at their data, basically they were using kind of like a statistics. They say, oh, we have a little bit warmer than 0 Kelvin. What is 0 Kelvin? I don't know. But anyway, they didn't really get it. So 0 Kelvin is called absolute zero. And absolute zero corresponds to this Celsius temperature and this Fahrenheit temperature. One of my I have lots of little pet peeves. I bet you guys do too. I went to Chicago at the Adler Planetarium, and they had how cold or warm it was on the planets. I'm like, oh, that's cool. A little information about the planets. And for each one of them, they showed a complete temperature scale. And the lowest temperature in all the temperature scales was negative 300 Celsius. That made them mad. I'm like, really? So anyway, I meant to send it off to Neil deGrasse Tyson. I haven't done it yet, but that just is not right, okay? Because negative 300 Celsius, it just hurts my brain. That would be colder than zero, absolute zero. So I want to show you, talk you through the whole Fahrenheit Celsius conversion. If you go into, see the doctor, a lot of times in a little triage room with their nurses, they will have like a little thing that converts between Fahrenheit and Celsius. And you can do it on Google. I don't put it on a test. What I do put on the test is converting between Celsius and Kelvin. Celsius and Kelvin, yes. Celsius and Fahrenheit, no. And I say I put it on the test. It won't be a specific question, but you'll have to be able to do that as you work problems. So I'm going to actually talk about different levels of, different sophistication levels of measurements. So you're going to see an interval level and a ratio level. Ratio level is very awesome. Interval level, it's okay, but not as good. And as it turns out, Celsius is an interval level and Kelvin is the ratio level. So here we go. Here's our options. I'm going to talk you through these different sophistication levels of how do you measure something. The first one is actually no numbers, okay, non-numeric data, and you just divide people into classes. So I could have people with brown hair, people with black hair, people with blonde hair. Well, it's not a good example here because I'm blonde hair. But I could go ahead and group you guys, okay? It's one way to kind of sort you out, but it counts as like a type of scale. What really to me makes it a scale is to take non-numeric data and then to go ahead and apply some sort of ranking. So I could say blondes are smartest and brunettes are less and people with brown hair are in between. I don't believe it, I don't believe it. But I could go ahead and give some implied ranking to something that's non-numeric. It could happen, and it's out there, I'm sure. Not in science as much. Then there's the interval. And the interval actually has numeric data, but if you look at the 0 on that scale, there's not much to it. And case in point, we could choose either the Fahrenheit or the Celsius scale. I'll go ahead and choose the Celsius scale. And a little bit ago, we had 100 degrees Celsius, water freezes. Water boils. And we had 0 degrees Celsius, water freezes. And then, can you have a negative 10? Heck yes. Can you have a negative 100? Yes. Can you have a negative 300? No. Okay, but my point here is that 0 on the Celsius scale, who cares? It's just kind of a number in a continuum of positive and negative values. Fahrenheit the same way. So it is numeric, but the 0 doesn't count for nothing. Okay, no offense. And then the best one is the ratio. And honestly, in science, we do a lot with a ratio scale. Here's the deal. It's numeric, and the 0 means something. Aside from temperatures, for instance, we could get out a ruler, and of course, all matter has mass and occupied space, but we could get out a ruler, we could say that it's 12 inches, or 24 inches, or we could say it's 0 inches. Basically, 0 length. You just kind of really think about it. It's an object. Okay, so 0 means something when we're measuring length. Okay, on the Kelvin scale, does 0 mean something? Yes. This is 273. This is 373. Okay. And down here somewhere, negative 273 Celsius, we have 0 Kelvin. So that really has significance. If I said 0 centimeters means no length, then 0 Kelvin means no temperature. It means you put your thermometer in that, and rose to you, there's no pings, there's no motion that's making that thermometer go up. So 0 Kelvin is the absence of thermal energy, the absence of molecular motion. So anyway, it's pretty exciting. So the true 0 that's part of the ratio scale means that it's absence of whatever it is, if it's length or thermal energy or whatever. So we can take length here, for instance. If you have 0 centimeters or 0 inches or 0 feet or 0 meters, those will all be ratio levels of scales. This is just kind of showing you kind of a logger pro sort of approach to graphing Fahrenheit temperatures versus Celsius temperatures. So 0 Celsius is 32, so there's 32-ish, 32, and here's 0. Okay, so that's the temperature at which water freezes. Up here we have water boiling at 212 Fahrenheit and boiling at 100 Celsius. So given 2 points, with 2 points you can make a straight line. We have a straight line.
And then that line actually would be great for going back and forth between the Fahrenheit and the Celsius temperatures. If you know about that, the way then we can take the information that's given in with the slope of that line and the y-intercept's 32, slope is 1.8, and we can use those to actually, in equation in just a minute, kind of knock out going back and forth between Celsius and Fahrenheit. And this is what it looks like. Okay, so this says if you want this and you're given this, that's what you use. If you want Celsius and you're given Fahrenheit, that's what you use. Now, again, I'm not going to have, you might have to do some of these homework. It's a smattering. My favorite way, if you've got a computer handy, is to go to use the Google. And just remember how we can convert between like pounds and grams using Google. We can also convert between temperatures using Google. This is just when I Googled convert from Celsius to Fahrenheit, this is what I came up with. So if we have 100 Celsius, that's 212 Fahrenheit. What is negative 40 Celsius? Negative 40 Fahrenheit. Let's put negative 273. Okay, ooh, let's put negative 300. Wow. Well, see, you just can't do it. Okay, so negative 300 is colder than absolute zero. Ah, silly Google. So anyway, so I've got some examples. Oh, by the way, down here, the 1.8 that you see in the equation and the 32 actually are exact. So here's an example. If we want to go from 25 Celsius to Fahrenheit, what we would do is plug in our 25 Celsius right here. So then it's going to read 1.8. Notice I kind of blow off my units. 1.8 times 25 plus 32. And that gives you 77 degrees Fahrenheit. It's weird because you might be reading this like, I bet the 1.8 degrees Celsius? No, I mean 1.8 times your Celsius temperature. And then you get into like how many sig figs, and you're adding, you're multiplying, you're adding. Oh, it's just a mess. Okay. Next one must be Fahrenheit to Celsius, and it looks like this. So we're going to take this 98.6 Fahrenheit and we're going to plug it in right there. So what it looks like is in the numerator, to get to your Celsius temperature, you're going to have 98.6 minus 32. 32 is exact. And that quantity is divided by 1.8. And I can sort of see why I'm giving myself 3 sig figs, 37.0 degrees Celsius, because of the 3 sig figs I started with. All right. So a little bit more about that Kelvin temperature scale, which is the ratio temperature scale, the most sophisticated, the one that has a zero that actually means something. You actually mean something. Okay. Sometimes Kelvin temperature scale is called the absolute temperature scale because 0 Kelvin is absolute zero, the lowest temperature possible. So 0 Kelvin means that there's no thermal energy. Thermal energy is a function of the motion, and all matter is motion. So you're like, really? How does that work? Anyway. So this actually, I haven't done it for a while, but these actually you should get under your belt. So I would memorize this. Memorize this. And again, since this is Gen Chem instead of Intro to Gen Chem, I'm probably not going to just ask you to do this. It's going to be part of the problem. So a lot of times your temperature is given in degrees Celsius. So you are going to add 273 units to it. If your temperature is given in Kelvin, then you're going to have to subtract 273 to get it to Celsius temperature. Okay, so negative 273. I say 273, but notice with 5 sig figs or with 2 decimals, it's 273.15. Okay, and we are done. And so this homework is due on Wednesday. I don't think it's too bad though.